degrees isn't actually relevant to what we're doing. That's the angle we're trying to find. We've got our platform or our conveyor belt, which we know is 9 meters long. So this thing is 9 meters. And we are trying to get the angle when I put that ramp up to a platform that is 4 meters above the ground. So we know we're going, what's up? No, it's the one from Tuesday, the previous one. That one. We can go ahead and assume that the building is in fact at a right angle with the ground. I'm going to assume it's not the Leaning Tower of Pisa. They would tell us if it was a weird angle. So if I want to know the angle here, what pieces do we have? We have our hypotenuse and our opposite side, because we want to have this angle. Because this is my little truck down here. They usually have these things on like a... Ooh, I'm so good at art. Here's my truck. Ta-da! Those little trucks drive around the airport. That they look really fun to drive. Because they're like really small and really fast. Those look so fun to drive. So, if I know my opposite side and I know my hypotenuse, which trig function should we use? Sine. Because sine of an angle is going to be our opposite over the hypotenuse, right? So sine of this blue angle, theta, is going to be opposite, which is 4 over our hypotenuse, 9. How can I figure out what the angle is? Inverse sine. To undo the sine, we need to take the inverse. So if I take the inverse sine of both sides, we're going to wind up with our theta equals the inverse sine of 4 over 9. And we need to type that in the calculator. They do specify that they want this as a degree, so we need to make sure we're in degree mode. They say that up here, to the nearest degree. So we need our calculator, which is going to look like I delete this. I promise I'm not. I'm just switching to the computer so I can get the calculator up. Okay. It's going to think for a second. There it goes. Don't change the fraction. It stays the same. We're just like if we would add or subtract to both sides of the equation, we can take the inverse of both sides of the equation. So we need to do inverse sine. So these are one. Sine is here, so we need to make sure we take the inverse. So we're going to do second sine 4 over 9. Make sure you're in degree mode. Since they asked us for degrees, we need to make sure we're in degree mode. So we should get 26.387799996. They did tell us in the question to round to the nearest degree.
So
26 degrees. So our angle is going to be 26 degrees. Okay. Questions on that one? Let's do the other one from this day, and then we'll finish out the ones for the bearings from yesterday. I figured easier to warm up with these guys than to hop straight into bearings. Bearings are weird. All right, so we've got a ladder that's 20 feet long leaning against the side of a building. So I've got a building, probably against the ground. We can go and assume it's at the ground. And we've got a ladder that's leaning. I know my ladder is 20 feet long. And we're given an angle this time. The angle again with the ladder and the building. So where the ladder connects to the building is this guy, is 22 degrees. We are asked to figure out here in part A, the distance from the bottom of the ladder to the building. So we want to know what this distance is down here. The distance between the bottom of the ladder and the side of the building. That's what we want to know. So looking at our triangle here, what pieces do we know relative to this angle? We know this guy's our hypotenuse, right? And we're looking at our opposite side here. So if we're looking at our hypotenuse and our opposite, which trig function are we going to think about? Opposite hypotenuse?
Oh, cosine.
Cosine. So we can use any of the trig functions for some of these. We will bounce around between them.
Wait.
Because cosine, I'm just going to write cosine of an angle, is our opposite over hypotenuse, right?
No, this is
Cool.
sine.
Oh, yeah, right. Oh. Sine. There we go. I was going to say, we were just kind of trucking with it. Call it out. Because you know what happens? Someone will have that thought in the homework and they'll just keep on trucking. Look back at it and make sure we're thinking correctly about what we're doing. That'll be one of those most common mistakes we get is we'll just be like, it's cosine. Power through. Double check. Sine is opposite hypotenuse. So, toa. Bless you. So we know, looking at this specific situation, that our sine of 22 degrees is going to be equal to our opposite side. It's a guy we don't know. That's our x over the hypotenuse. 20. How do I figure out what x is? Multiply each side by 20. So we're going to have 20 times sine of 22 degrees equals our x. So how can I get like an actual distance here? Calculator. If it was an angle that's on the unit circle, you can get your value that way, but 22 degrees is not one of our unit circle angles, so calculator it is. So we're going to take our 20 times our sine of 22 degrees. Again, make sure you're in your degree mode if you're not. So we're going to take our 7.492131868, and we can go ahead and take one decimal place, nearest one decimal place, nearest tenth. So we're going to give it 7.5. So our x is going to be 7.5-ish. Same unit, so 7.5 feet. So this equals 7.5. Then we're asked in part B to approximate the change in elevation, or otherwise known as the height, between the ground and the top of the ladder. So we want to know this distance. How can I find that distance? Absolutely valid. We would need to know this angle. So we could take, if I want to do this as alpha, you could absolutely do that. You could do our cosine of alpha would be what? What's cosine going to be here? 7.5 over 20. That is an absolutely valid way to approach this. It is kind of the hard way, though.
But can we just figure out what it is by subtracting 180? Like, you're doing like 180 minus the 22.
to get the angle that way? Yes. Remember, we're not actually looking for the angle. We want the height. Pythagorean theorem. I was going to say, you can do it this way. Y'all are going the real hard way, though. Because this is a right angle. I know 7.5 squared plus our y squared is going to equal the 20 squared. So you can absolutely go this way, but it's the hard way. A slightly less hard way, but doing the same thing would be if we did our cosine of 22 and did y over 20 and did it the very same way we did at the top. That would also work. But honestly, I still think Pythagorean theorem is the easier way to go. Because our 7.5 squared gives us what?
56.25.
56.25 plus our y squared equals 400. So figure it around, go to all the way down. What is our y going to equal?
3, 4, 3. Oh, wait.
So y squared will be the, yeah.
18.5.
Yeah, it should be about 18.54. Which if you left this as a slightly longer decimal, you'd actually wind up with the exact same answer here. So make sure we're paying attention to what we're looking for, because we don't necessarily have to solve this triangle entirely and find all three angles and all three sides. They did want us to find all three sides, but we didn't really even need the other angle. But the height of this building is 18.54 feet. 18.5 feet would also work. Okay? Throwing stuff. Questions on this one? Let's finish out looking at our bearing questions. Okay. So these are the rest of the ones from the yesterday questions. Anyone need a copy of the yesterday questions? They don't have it, or they lost them. This is the one that had the pilot that's starting. Oh no, that was that was one that had the plane that was 80 miles at the top. We only got through the first two yesterday. Okay. So we've got an airplane that's 30 miles northeast of the airport. The angle of depression from the plane to the airport's runway is 32.5 degrees. We're asked to find the altitude. This one is in fact not a bearing. This one's just an airplane story. So what we have is an airplane. You get to see my beautiful art again. Airplane, boop. I'm so good at art. It's a beautiful airplane. It's 30 miles away from the airport. So we know if they use their little scanner thing and they scan to the airport, they are 30 miles. This is my airport. We want to know how tall, how high this plane is. We want to know our altitude. What we know is the angle of depression. So what that means is the pilot's looking out the window and he's looking down to the airport. This angle is the one we know. So if the plane flies along here, this is what the pilot looks at as straight ahead. This angle is the one that is 32.5 degrees. And we want to know the altitude. So we think about our altitude being straight down from the plane. It is also the exact same as if I came straight up to the airport here. Whichever way we think about it, we should be able to get the same pieces of information. I tend to think about it this way, but if you want to do it here, we could do the exact same thing. We would have a set of vertical angles. Oh, snap, what? We want to know our altitude. So if I want to know A, I want to know this piece, and I do know this angle, and I know this distance. What can I use to get A? Mm-hmm. Yeah, because we know our opposite and our hypotenuse. Now that we're feeling a little more confident there. So we know that the sine of our 32.5 degrees is going to be our opposite, A, over our hypotenuse, which is 30. How do I figure out what A is? Multiply by 30. We're going to have our 30 times our sine of 32.5 degrees gives us our altitude. What is our altitude going to be? 16.1, as going to be 1, 1, blah, 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 blah. 16.1, what's?
Feet. No, miles.
Miles. You got plane flying at 16 feet, we'd probably have problems. Unless it's coming in for a landing. Hopefully it's coming in for a landing, but if it's 30 miles from the airport, that's probably still problems. That is definitely meant to be an equals. There we go. Okay, so a lot of times on these, it's the placing of the pieces on our picture on our triangle that makes things weird. So we got to try and read the question carefully. Okay, let's look at our next one. We've got an airplane that is 15 miles from the airport. This time we do have a bearing. At bearing north 62 west. So that is saying from the airport, they took this bearing. So my airport's in the middle. So we're going to look at our airport. Whichever airport that is. We don't know which one it is. And if they go from our airport north 62 west, thinking about this as a coordinate plane, which quadrant are they going to be in? 1, 2, 3, or 4?
1. 2.
2, because remember, we're going to never eat those soggy waffles. So if they are based off the north axis and they go to the west, we're over here in quadrant 2. So they went this way 15 miles. We know that our angle is based off of the north axis, so this guy is 62 degrees. What they're asking us is exactly how far west they go. We want to know this one. And then exactly how far north did they go. So we want to know this side. North and west meet at an exactly right angle. So we have several pieces here of this triangle. I have an angle, I have a hypotenuse, and we're looking to find both of the legs. What's up? What's your idea?
We take the sine of 62.
Mm-hmm.
It would be W over 15.
Mm-hmm.
And multiply by 15.
Mm-hmm.
And then we can just see
Yep. So I'm going to write some things down. So yes, you're exactly right. Because we can take our sine of that angle, 62 degrees, and that's going to equal our opposite over hypotenuse. So in this case, we're going to get our W over our hypotenuse of 15 to set up that sine. Exactly right, that we can multiply by the 15 to get that W by itself. So we're going to have our 15 sine of 62 degrees equals our W. So exactly how many miles west are they from the airport?
13.
Yep, 13.24 or 13.2. 13.2 miles. How can we figure out how far north they are?
Beside that.
You could do cosine, or you can do the Pythagorean theorem. Both are equally valid. So I'm gonna set up the cosine one just so we can see it, because we haven't seen a cosine one. So if we did our cosine of the 62 degrees, that would give us our adjacent over the hypotenuse, so that would give us n over the 15. It genuinely does not matter which one of these you do. You can even do both if you feel like it. Totally fine. It should give you the exact same answer as if we do Pythagorean theorem. If not, it'll be off by minutia of decimals. So you can either do that, or we can take our n squared plus the 13.2 from the w squared and equal it to the 15 squared. Either way is fine. How many miles north are they from the airport? 7.04. And if you have slightly different, because I hadn't double checked it with the Pythagorean theorem, but it should absolutely work. But if you do it with this, it should wind up as cosine of 7.04 miles. I was going to say, it'll be off by minutia of decimals. It'll be close enough. And that's just because we rounded this instead of taking the forever long decimal. That's the only reason that's off a little bit. Okay. What's up? Oh, this is two separate pieces. This is if we did it with cosine. This one's if we did it with Pythagorean theorem. Two different ways to approach it. Two separate problems. Because we would move to 15. This is just Pythagorean theorem. And it genuinely does not matter which one you do. It's just I heard both options at the exact same moment, so I was putting them down so we could see that we have it set up right. Okay. Let's do another one. This one is asking slightly more. So we've got a plane that's flying east at a constant altitude of 3,000 or 30,500 meters. And we've got a person on the ground watching it. So what we have is we got a human. Ooh, that's not a pen. Come on, pen. Stop being a jerk. We got a person. Ooh. And we've got a plane that's standing to the east, or that's flying to the east of the observer. Airplane. When they first see the plane, that is the worst straight line I've ever drawn. Ta-da. We know that it is at that 65.6 degrees. And we know that its altitude is at that 30,500 meters. Then what they have is they keep watching the plane, and as it flies further and further away, the angle gets lower because my plane's further away. So we're gonna have our plane that keeps flying, and now it's over here, and our angle is changed. It's flying at the same altitude, but now we're looking at this little angle here. So I'm gonna name them. I'm gonna say that the first angle was our alpha, that was 65.6. I'm gonna do this yellow angle as a beta, and it is our 56.1. We are trying to figure out how fast this plane is going, which means we need to know the change in the distance here. This plane is flying at a constant altitude, so this one's at the exact same height. That's a comma. And we're trying to figure out the change in the distance here. So what we're gonna do is we need to figure out this distance here on the green triangle with our 65.6 degree. And we're gonna need to figure out the distance on the yellow guy from over here so we can figure out how it's changing. So X, G, and I'm gonna call this one C for change. So looking at our green triangle first, if I know my angle, I know my altitude, and I wanna know this, which trig function are we gonna use? Tangent, because I know my opposite and I'm trying to find my adjacent. So for our green triangle, we can use our tangent of 65.6. That's going to equal to opposite over adjacent, our 30,500 over that distance. What do we need to do?
Multiply x by both sides and divide tangent.
Yes. Multiply both sides by x and then divide both sides by tangent of 65.6. So we're going to wind up with x equals our 30,500 over our tangent of 65.6. So the distance, when this person very first sees the plane, the distance between him and that plane is going to be what? Mm-hmm. 13,000. We can go ahead and take it as whole numbers here just because otherwise it's going to get even grosser. 13,835. So then what we're going to do is we need to find the distance on the yellow triangle. Same vibe. And in fact, I know this same pieces. I know my angle. I know my opposite side. So we're going to do the tangent of the other angle. We're going to take our tangent of beta. Tangent of that 56.1. Okay. Thank you. And that's going to equal our 30,500 over our distance. We're going to follow the exact same process, multiply by our denominator here, divide it by the tangent. To get our distance is that 30,500 over the tangent of 56.1. And so the distance here is what? 495. So how can I figure out the change in the distance? Subtract them. So the change of the distance is going to be what? 6,660 meters, right? How does that help me find the speed of the plane? What do we need for the speed? Distance over time. How much time did it take for it to move that 6,660 meters? 33 seconds. So our speed, we're going to get from our 6,660, there we go, meters per 33 seconds. So what is that really? What's our speed? Meters per second. 201.81 meters per second, which we're going to round up to be 202 meters per second. So sometimes they will combine things together. We have to find the change in the two triangles, finding the difference. The other way they will give us tricky ones, it's not written on your paper, but it's very, very, very much like question 63 on the homework, which is annoying. Okay, so let's We're gonna look at this one. It's not typed out for you. We're gonna work this one. This is our last one for today. We're not do that last one just because I'd rather us do this one. We've got a ship that leaves port at 1 p.m. and sails a certain bearing at 22 miles an hour. Then the other ship leaves port at a different bearing at 20 miles an hour. So I'm gonna draw it out over here. So we have a port, which I need a pen. Port. And again, we think about our never eating soggy waffles. So if our first boat, I'm gonna do purple, sails at north 25 west.
Quadrant 2.
Mm-hmm. So it's gonna go this way. And this angle is our 25. Just gonna make this line up a little bit longer. So I've got a boat over here. My beautiful purple boat. Ta-da! And then another ship, I'm gonna have it be green just so they're visually, that leaves north 65 east. So still based off of north, but now this one's headed east, this way. Here's my other boat. Apparently it's a very deep boat. It's a very tall boat. And we're at 65 east this way. I need to move my 65. That's gonna be in the way. 65. There we go. What we're asked to find is how far apart are the boats? This is the distance we want to know. So what we need to find is I need to figure out what this distance is here. How long did it travel between when it left at 1 for the purple boat and when it arrived at 4 p.m.? How many hours did it travel? From 1 to 4? Looking at purple. 3 hours. And how fast was it going? 22 miles per hour. So how far did it go? 66 miles, right? 3 times 22. So this side is 66 miles. How far did our green boat travel? 2 hours and 30 minutes, which is the same as 2.5 hours. And it's going 20 miles an hour.
20.5.
Mm-hmm. You think?
50 miles?
50. Yeah, I was gonna say, close, but not quite. 50 miles. These two angles combined together, 90 degrees. Oh, that makes this guy a right triangles, and we're just trying to find that hypotenuse. What?
Free cheese.
Free cheese. That's a new one. Okay, so since we have a right triangle, we can use the Pythagorean theorem here to find that distance. So the distance between the boats we can get from 66 squared plus our 50 squared. Those are the two legs of our right triangle, and we want to know what the distance is. So how far apart are they?
82.8 miles.
82.8 miles. That, I have way too many decimal points in that one. What the heck was that? 82.8 miles. The tricksy part of this is figuring out the bearing from the purple ship to the green ship. What we need is I want to know what direction to take on that black line right there. What is this angle here? right here. I've got a set of parallel lines. 25. It's a alternate interior angle here. Old school geometry. This guy, since they are opposite of two parallel lines, old school geometry property. This one is also 25 degrees, alternate interiors. Because the north-south is parallel to the north-south, so those are parallel lines, and they're on the same segment. Then we can find out this angle for our right triangle here, because I know any number of sides. I know both the adjacent and the opposite and the hypotenuse. I can use whatever the heck trig function we want to find this blue angle, because what we need to find our bearing, and we have 3 minutes, so I don't want to talk all the way to the end, is I need this angle to be able to decide south, whatever that angle is, to the east for our bearing. Okay, let's do it real quick. All right, so blue angle we can find. Let's do, I'm just going to grab sine. Sine of blue angle, opposite, 50, bless you, over our hypotenuse, which is 82.8. So do your inverse sine of 50 over 82.8. What is that blue angle? Whole degree. What was it?
Wait, you just like, you right back to 2.8. They're gonna put sign in it.
Yeah, you do the inverse sine of 50 over 82.8.
I got syntax error. Wait, I'm doing it wrong. 37.1. Yep.
There we go. I'm going to go 37 degrees, right? So if I know the blue part is 37 and the pink part is 25, combined together, we're going to get an angle of 62 degrees. So this purple boat needs to go south 62 to the east to get to the green boat. Green boat gets broken down. Purple boat's coming in to rescue. Okay? Not a great name. I have, if you're ready for it, the chapter review. We have like a minute to the bell, so I'm going to put them here, just in front, out of the way. So they're there. That is everything for the whole chapter. Tomorrow we will work with the review. Y'all can ask questions, y'all can have work time, whatever we need to. It's because there's lots of space. You scrubbed a whole heap of them, man. Bell's about to ring. So I put them by the door, then got out the way.